It is a great honor to introduce Professor Stefano Stramigioli, a full professor in advanced robotics, leading a growing group of about 60 people. He is an IEEE Fellow for contributions to modeling, control, and realization of complex robotic systems, and a member of the Royal Holland Society of Science and Humanities. He is an ERC Advanced Grant and Proof of Concept Laureate, designed for ERC-funded researchers to validate and commercialize their frontier research innovations. His research is characterized by energy-based techniques stemming from ideas of bond graphs and port-Hamiltonian system theory, which he brought and vastly used in the field of robotics. His remarkable career has been defined by groundbreaking contributions that seamlessly integrate sophisticated theoretical framework with practical, meaningful applications. As an example, I could mention the idea of energy tanks and the dual architecture for telemanipulation. He has around 450 publications, including 4 books. He has been, among others, editor-in-chief of the IEEE Robotics and Automation magazine, advisory committee member of the IEEE Robotics and Automation Society, founder and chair of the Electronic Products and Services of the IEEE Robotics and Automation Society, and he has been serving as vice president for membership of the same society for 2 consecutive terms in the past. Today, Professor Stramigioli will share his invaluable perspective in a talk titled Port-Based Thinking in Modeling and Control of All Physical Systems, where he will introduce the basics of such ideas and show their power in modeling the complex interaction of a fluid and the deformable elasticity of the wings of a robotics bird. Please join me in extending a very warm welcome to Professor Stefano Stramigioli.
Thank you very much for your kindness. Thank you for being here. Well, it's actually a big honor to be here, and I would like to thank the organization for inviting me, because actually in '93, my very first paper, just graduated in '92 from the University of Bologna, I presented my graduation thesis as a paper at ECC in '93. So that was my very first paper, so it's very special to be here. So, I want to start, physics. I'm doing a lot of stuff now in theoretical physics. And in physics, symmetries are really the guiding line of everything. And gauge fields are all particle physics is based on this stuff, basically. Energy and a mathematical embodiment is the mathematical embodiment of these symmetries. I'll tell you more about later. Physical interactions between machines and humans or the environments is at the core of everyday's life. And mathematics is definitely the most powerful tool that engineers have at their disposal. And yet, most of the time, energy is completely ignored in what we do. And mathematics is not taken seriously, and physics certainly is not taken seriously. So what I want to do is a kind of tutorial-like. I want to actually give you, and there will be some math, but on certain things, so we'll be technical in certain points, but I hope to give you an idea why you would be willing to look at this stuff at first place. And I will be here the whole week in case you have any questions. So this has been a guiding line in everything I've been doing in my career. When I went to the Netherlands, because my wife, then girlfriend, was Dutch, that's the reason why I moved to the Netherlands, I had to work on this stuff, bond graphs. I didn't get the point. And then at a certain point, I understood what is the power of these things, and I cannot think if I don't frame it that way. And there are reasons for that I hope to share with you. Okay. And a lot of things, telemanipulations, solving time delays, is all based on this. Eventually, if something gets unstable, it's because you pump too much energy into the system, if it's a physical system. And people don't even look at it. So I want to first play a game with you guys. You know what this is? And some people may have seen this talk or part of it, but this is called a dovetail. Okay, it's a mechanical thing. So if you go to IKEA, you buy something, you want to assemble 2 things, you have a red part and you have a gray part. Basically, this kind of motion constrains 5 from the 6 degrees of freedom, right? And one is, so you assemble it, and then you put a screw, you fix the last degrees of freedom, you have the 2 things fixed on each other. Now, here's the question. can these two pieces move? Who's for yes? Who's for no? A lot of people do not dare, but you see the majority is no, okay? Well, it's too bad for the no guys, okay? So what's going on here? You see, you made an assumption on the thing just by looking on its outside, but you didn't see what was behind, right? Now the second question, now you're thinking longer, says, are there other possibilities? Of course, there is a symmetry of, discrete symmetry on the other diagonal. Are there more? Oh, yeah. Okay? So, and there is a last one. I mean, there are a lot of possibilities. All these possibilities are all the possibilities that you have by thinking what you didn't see. Okay? So, what I want to say here is, one second, there's another one. What I want to try today is to bring you out of this, to let you experience this, because sometimes there are things out there, well, behind the block that you don't see, and maybe a solution to your problems, okay? And I think the port-based ways has changed my life, scientifically without any doubt, and brought me to what I consider very, very important contributions in physics. And by doing that, I like nature, I like to look at things. Aristotle said, in all things of nature, there is something of the marvelous. And being an Italian, of course, I could not leave out to talk about Leonardo, who's been studying flights many, many, many years ago, more than 500 years ago. Okay. Birds are amazing creatures, but the physical interaction is pretty nasty. You have basically fluids, Navier-Stokes, nonlinear PDEs. You have flexible stuff, is also nonlinear PDEs, and then you have these two nonlinear PDEs that actually interact by a boundary, the wing surface, which is moving in this space. Now, more complicated than that, I don't know. Can you properly find a way to do it? Yes, and I'll show you how. Okay? So I will talk about port-based thinking, talking about the Port Wing project, which is the ERC grant I had the pleasure to run, which is finished 2 years ago, one year ago. And in order to do that, I want to show you something which you may know, or has anybody ever heard about exterior calculus? All right, very good. So basically, I will give a mini tutorial on this stuff, and then show you why is that important, to at least trigger you to look into it. So this all started, because you know these guys? Okay, Jamie, actually, I gave them laurea honoris causa a few years ago, and Jamie is a good friend, especially. Adam is not much, but Jamie is a very good friend. And we started a project related to flight, okay? And then from there, working, we actually have been involved in this project, which is pretty amazing. This is unique in the world. For those of you guys who were at IFAC in South Africa, you remember this festo bird? This is much faster. This can fly where festo birds would fall out of the sky. This goes at 80 kilometers an hour. I mean, what they do at festo is absolutely magnificent. I don't want to, but this bird is really very special. It can go at 80 kilometers an hour, 5-foot wind. It waits like a falcon. It flaps at the same frequency as a falcon. And it's pretty amazing. And this has been recognized in different places. And we got the Tech Transfer Award in 2016 and Best Paper Award, etc., etc. But I like to understand why things work. It's not just nice to see and build something. And there is some hypothesis that, if you fly a plane, you have a steady flow on the wing, okay? And steady flow of the wing means, there are no turbulences. You don't want turbulences. Instead, birds, they create vortices all the time. That's how they fly. So they basically change the angle of attack, creating these vortices. And if you see down left, by creating these vortices, they shed them, and they create jets. So basically, the propulsion of the bird is created by creating these vortices that create jets, and that's how they propel themselves. And it turns out that actually all flying animals and all swimming animals actually work in a regime which has a certain regime of what is called a Strual number, which is an aerodynamics coefficient, which is independent of units, which is given there. Okay? And these are hypotheses because this is 2D. These are computational in 2D. But I wanted to understand and model the physics in 3D, And not only like this, but with a moving, flapping wing. So this is much more complicated. And why and how does it really work? So only understanding this, we can systematically improving and do maybe control and stuff like that. You know who's the guy behind? No? Wittgenstein. Wittgenstein said, what we cannot speak about, clearly, we must pass over in silence. Okay? Unfortunately, I'm pretty sure that a lot of politicians never heard about Wittgenstein. Okay? But what I think is that in order, if you want to talk about flapping flights, you really need to really dig into the mathematics and trying to understand things from a geometrical point of view. And so the project was divided actually in two parts. You know, as Aristotle divided techne and episteme. The techne is more the technology, the engineering part, and what I will talk mostly will be the episteme part, so really the conceptual understanding of this. And if you have a robotic bird, you know, the rigid body is a rigid body. We know how to model that properly. You know, SE3, small SE3 cross SE3 star are the Lie group, the Lie algebra and its dual. It's the pair that describes the power flow in multi-body systems, rigid multi-body system. We know that. But of course, things get much more complicated once we want to talk about the wing interaction with the fluid, as I said, okay? Because then you have Fourier Navier-Stokes, let's leave the thermal out, Navier-Stokes. And then you have a variable boundary because the wing is not rigid, it's flexible. So the wing deforms in the air and moves around, and the air around created turbulence and all this stuff. So it's pretty complicated, okay? So how to do it? Well, it turns out that we needed some new mathematics and some new concepts to be developed. And he brought to what are called tensor value differential forms, which actually is something that is known. Okay, it's mathematics which is known, but not used in the way we did it. Okay, and before going to that and doing some other stuff, I want to show you a video of the project.
Nature is amazing, and
can the volume go up?
Amazing creatures, but we do not fully understand yet how they can fly. Could we really understand the magic of flapping flight so that we can build robots that can fly better than the robots that are currently available? The Robird is the only robotic bird in the world which can fly in up to 5 Beaufort wind and at a speed of 80 kilometers an hour. It weighs the same as a peregrine falcon, and it looks like it, but do we really understand the underlying physics? We believe that flapping flight is achieved with a combination of flapping and twisting of the wings, which creates detached vortices which generate thrust. But are we at the moment using the optimal combination of the oscillatory pitching and plunging motions of the wing? To answer this question, an experimental setup is built in the wind tunnel of the University of Twente to see how the wing moves and how the stream of air moves around the wing while it's flapping. This allows for exploring the optimal wing motion for the Robird. A helium-filled soap bubble generator is installed which blows thousands of bubbles per second into the wind tunnel. 4 high-speed cameras film the bubbles to capture the movement of air around the wing with the shedding of vortices. Furthermore, a force sensor at the root of the wing can measure the resulting forces on the wing, like lift and thrust, and reflective markers on the wing can be filmed with cameras to track the wing movement and deformation at a sub-millimeter scale. We have studied the flexibility of the wing since it's an important part of why the Robird flies the way it does. Different than many people think, intelligence can also be embodied in the material and properties. A brain without a proper body is useless for locomotion. We want to bring this physical intelligence in the wings of a robotic bird, and in order to do so, we created smart wing designs and smart mechanisms which are able to change the mechanical stiffness of the wings to change the flying behavior. But how can we precisely describe the physics of a robotic bird with deformable wings interacting with the air around it? The unique feature of the approach we followed to describe dynamical physical systems is that it relies on energy and geometry. Energy is probably the most fundamental concept unifying the various branches of physics and explaining how nature works. In the Port Wings project, we used the port-Hamiltonian framework to get insight into the energetic fundamentals and transport phenomena of fluid dynamics, structural dynamics, and fluid structure interactions. In the port-Hamiltonian framework, we describe any complex physical system as a network of energetic modules interconnected using power ports that characterize the energy flow within the system or exchanged with the environment. For example, if we consider the flapping wing setup we developed, we describe it as a network that represents the dynamics of the driving mechanism, the elastodynamics of the wing, and the aerodynamics of the air around it. The power supplied from the power source flows to the electric motor, and then some of it is stored as kinetic energy in the mechanism's inertia. Some of it is dissipated as heat and noise, and the rest goes to the flexible wing. The power supplied from the wind tunnel is also transferred to the wing through the moving boundary of the wing and the airflow injected inside the wind tunnel. In each cycle of the wing's flapping, the power supplied to the wing oscillates between kinetic energy and elastic potential energy, while the power that flows to the air is either stored as kinetic energy or dissipated in the vortices formed due to the wing's flapping motion. Our port-Hamiltonian description of this physical system differs significantly from the standard approach of continuum mechanics using coordinate-based tensor calculus treatments. We rely instead on coordinate-free exterior calculus and describe the network structure of the system using so-called Stokes-Dirac structures. This methodology allows us to intrinsically handle open boundary conditions and thus use, reuse, and combine submodels in such a way that a real Lego of physics would be possible. Consequently, this leads to the development of structure-preserving computational algorithms that allow us to efficiently and robustly simulate these physical systems to produce predictive computer models of the world around us. The real advancements in science and technology are only achieved with a deep understanding of the fundamental theory, as well as proper engineering and experimental skills targeted to the goal to be achieved.
And what I said there is the person who was talking said it's coordinate invariant. And I want to play a game. This is like, he says, oh, come on, I'm a control conference. Do you have to ask this thing? Well, you'll be surprised, okay? Suppose we have this game. We have these two guys. These are not two stupid guys. We have Hilbert, one of the biggest mathematicians ever, a formalist. And we have von Neumann. He built the computer, and he basically did the whole mathematics which is needed in quantum physics, basically, just like that. And they collaborated because von Neumann actually was a student of Hilbert. And now they are in different places. They are not in the same place, and they get two matrices, 2 by 2, not too difficult. And they are not stupid. They know what you're saying. One gets a red matrix, and the other one gets a blue matrix, okay? And then I send them an email, suppose, it says, well, calculate the square of that matrix, okay? And then von Neumann does that's it. And then Hilbert says, silly question, I cannot calculate the square of this matrix. And they are both right. Do you see what's going on? Then I ask the inverse, and von Neumann calculate the inverse of this matrix. And David Hilbert does calculate the inverse of this matrix, but changes the color. It's not blue anymore. Is whatever color that is, okay? And then symmetric, and von Neumann says, I cannot tell you if that matrix is symmetric. It makes no sense. And David Hilbert does that. No, it's not symmetric. Can you give me the answer? Then I ask to calculate the eigenvalues. Von Neumann gives me the eigenvalues. And Hilbert says, silly question, they are not defined. Come on. And they are both right. Well, if you can calculate the eigenvalues, you know the determinant of a matrix, right? But if you cannot calculate it, there is no determinant. So Hilbert cannot give me a determinant. What the hell is going on here? They are both right. The problem is that this is the way this matrix transforms, and this is the way this matrix transforms. You say, oh, okay, you put an inverse, this transpose. That's the way nature works, okay? And the reason is very simple, because the one on the left is a numerical representation of the linear map from V to V. Instead, the quadratic form is a numerical representation of a map from V to the dual of V. A dual of V is the space of linear operators on V. It's a different space. Forces are not the same space as velocities. Forces are linear operators on velocity. If that you apply a force on the velocity, you get something which we call power. That's the way nature works. Okay? So, if you have a square of something that goes from V to V, you take another time V to V, no problem. But if you have something that goes from V to V star, you cannot use a map that goes from V to V star because you are in V star, you cannot start from V. You cannot do that. People do it all the time. There are a lot of papers which are conceptually wrong. Inverse, well, if you go from V to V, the inverse is from V to V. Doesn't change the color, but if you go from V to V star, if you take the inverse, you get from V star to V. It's a different color. Transpose, well, the transpose of a matrix represents what is called the adjoint of that map. So if the matrix may represent the map from V to V, the adjoint goes the opposite direction, Jacobian transpose, from V star to V star, in the opposite direction. And if you want to talk about symmetry, the transpose. So the indices are interchangeable because are the same kind of object, otherwise they are not. If I take a matrix, if it's a linear operator, what is defined, the way eigenvalues are defined is you just look at for the equation like this. If the map goes from V to V star, it makes no sense to define a map like that. Because you cannot multiply a vector for a scalar and get a covector. You cannot, you just make it longer or shorter in the same space. Okay? And so on and so forth. Well, you know, this is basic mathematics, okay? Wrong concepts which are used all the time. Manipulability in robotics is a wrong concept. There are people that spend their life working on this, okay? And there are reasons for that. Eigenvalues of an inertia matrix is a wrong concept. You change the coordinates of what you're using, you get different eigenvalues. What is that? A random generator is not something meaningful, okay? So mass matrices do not have that. And stiffness, for example, is something which you have very, very careful because it's only meaningful at equilibrium. Okay, and there are more reasons for that. I will not talk about it. You know, be aware of coordinates. Okay, it's really when you want to do some serious mathematics and physics, in my opinion, you know, let the structure be well understood. Coordinates can guide you in the wrong way. If you have the structure right, then you just follow the structure. It's very, very important, okay? And indiscriminate use of Rn can bring you completely on the wrong way, okay? And really let you make many, many mistakes, okay? So when mathematicians sometimes say a gentleman, or now gentleman or a lady, only chooses a basis and go to numbers if you really must. But it's better to be abstract and stay coordinate invariant. And this was a guiding line in everything we've been doing. Matrices are not mathematical objects. This has been known for centuries. There are many mathematical fairy tales that many people use, and 99% of the books teach you to, which are wrong. Do you know what this sentence means, or at least do you know where it is? Nullius in verba. This is engraved in all the scientific society of the world, the Royal Society of England, okay? And basically means don't trust anybody for it. So if you read a book, be critical if you read a book. That's what it means to be an academic, okay? And think about this stuff. So the core goal of Port Wings was to study the physics of the robotic bird in a decomposable manner and in a completely coordinate-free way, not falling into this trap. And you know who this guy is? Descartes. Okay, from him, one of the major figure in the history of mathematics. You know, he was the one who said, you know, if you have a complex problem, you need to decompose it, okay, and recompose it. Okay, and it's one of his treatments. So we tried to do this thing, and what we did basically first, we looked at Euler equations. We left the dissipation out. And we then dissected Euler equation in a completely covariant way, so without coordinates. That brought to a publication on the Journal of Geometry and Physics. And then we wanted to create advection, because advection is important for heat transfer, is important for compression and other stuff. And then was the second part of this work. And then we wanted to make a big leap to full Navier-Stokes. And in fact, we did it not only to Navier-Stokes, but we did it for Navier-Stokes and Fourier-Navier-Stokes, where also entropy generation and heat was considered. And that brought to the two publications in a Physics of Fluids, which is the #1 journal on fluids stuff. And then we wanted to really nail the big problem, which was, wait a minute, but if you have these two PDEs, which are open boundary, like, a Lego stuff, if the boundary moves, how the hell do you describe two PDEs that interact on the moving boundary? And we nailed it, and this was published again in the Journal of Geometry and Physics. And then, of course, the big thing was, fine, now we have a conceptual decomposition, but we want to do calculation with this. How can we do it? We want maybe to do, model reduction and then maybe control. And this brought to something which is probably one of the biggest things, I believe, in the whole story, which is a discretization of PDE, which is structure preserving. It is called the dual field method. And I will say a few words about this. If you use ANSYS, if anybody has used this kind of tools, if you do the grid is too small, you get instability and funny stuff, okay? Because the system is just not properly done. If you use our stuff, which is not yet available, there is a library, Pyham, which we wanted to develop, you give me two meshes with two grids, you get something which is the best you can get at that level of resolution, no instability whatsoever, okay? And then the last step was really to go to nonlinear elasticity, which we nailed it very, very well, I think. And this brought to a number of other papers. So what is all this port-based stuff? Okay, so there was first this guy, Henry Paynter, at MIT, who had the vision to really say, wait a minute, when we talk about physical system, there is always this transfer duality is playing a role. And he invented bond graphs. He was really the grandfather of bond graphs. And probably Bernhard and Arjan, I had the pleasure, when I was just a student to be involved in this thing, they brought this to a formal framework in a system theoretic settings, okay? And this has been the setting in which I've been working. I really believe this is more, my frustration toward universities and mathematics departments is that now we teach our students bad linear algebra. We tell them that linear algebra are matrix multiplications. That's not the case. As I told you, as I showed you. Matrix multiplications is just jungle-bungle with numbers. What is linear algebra is understand what kind of operators. A structure-preserving, a matrix is a structure-preserving map between two structures, okay? So if we would reshape things by saying, have a proper linear algebra, a little bit of differential geometry, we could just handle all branches of physics, from fluidodynamics, mechanics, electromagnetism, you name it. And even, now it's actually what I'm working on quantum and gravity, all of them in one single setting. You would see the relation between them at once. It would improve education enormously, but that's not done. What about symmetry? This lady is Noether, probably one of the best scientists ever. And because she was a woman, she didn't get a professorship. Okay, and Albert Einstein and Weil and other big persons were ashamed about the scientific community about that. And David Hilbert and Einstein said the most important woman in history of mathematics. Okay, she did much more than what I will cite her for, because the whole group theory that she developed has been groundbreaking and is still used daily. What she said is, in physics, if you have a symmetry, you have a conserved quantity. Of course, the concept of energy was born differently. But it turns out she really figured out, okay, that what energy is just a conserved quantity, which is due to the fact that physical laws are symmetric in time. So if I do an experiment now or tomorrow, it doesn't change. The result is the same. That symmetry is embodied in the fact that there is something which we call energy. And this goes much further than that. I don't have the time to go. So energy is very important. And Albert Einstein said that, all theories will be once forgotten. But if there is one thing that will not be falling apart is thermodynamics, okay? And I guarantee you that that's the case. And the work I'm doing now, which I cannot disclose yet, is precisely pointing that out. So port-Hamiltonian system is basically a kind of, was born from Hamiltonian theory. In Hamiltonian theory, you have certain structures, and in port-Hamiltonian theory, you have other structures. Then Arjan and Bernhard pointed out. Okay. And Hamiltonian theory is top-down. Physicists gets a big system, okay, and then they kind of cut it up and then they try to analyze it that way. Instead, in port-Hamiltonian system theory, you want to understand the atomic component of a system and then build it up from the bottom up. It's completely open. You know, Hamiltonian system is there. You can put some inputs, you know, a little bit, but it's not structurally. If you take another system, it's not a closed algebra. Instead, in port-Hamiltonian system, that's the case. Boundary can be open. Dissipation is not a problem, and all these things. Poincaré mathematics is the art of giving the same name to different things. What does that mean? Well, it means that if you study mechanics, okay, of a ball flying on space, you don't care about the color of that ball. So when you do approach a mathematical physical problem, you want to get rid of everything which does not meaningfully represent what you want to talk about. If you use Rn to do something, Rn has everything. Rn has an inner product, Rn has a length, but sometimes what you want to describe with this Rn doesn't have this property, so you are completely fooled by it, which is precisely what happens when people calculate the eigenvalue of inertia matrices, for example. Okay? So, in the 1900s, there was a big point in mathematics because Gregor Cantor, who invented the wrong set theory, because then it was fixed later, okay, because it was shown by Russell that was wrong, he basically also counted infinities, and that was a big thing. There were these two big group of mathematicians. David Hilbert is one of the biggest exponents of what I call the formalist, and Henri Poincaré of the intuitionist. And I want to use these two figures to make this difference, which is related to this game of matrices I did before. I will connect Hilbert to Hilbert spaces, to spaces that have an inner product, okay, to spaces which you have basically an isomorphism between vectors and covectors. Okay, you have an inertia matrix kind of stuff, but then infinite dimensional space as well. And duality connected to Poincaré. Poincaré duality, Poincaré studied a lot of stuff in duality. He was basically one of the godfather of algebraic topology, if you wish. Okay, and I will use these two figures to make this distinction. So first, duality in mathematics. If I have a vector space, what is a vector space? Well, it's the triple. You have a set, and then you have operation on this set. This satisfies certain axioms. And basically, you know, if it's finite dimensional, you have a finite basis, you can define these vectors. These are abstract vectors, they're not numbers. These are things in V, okay? And then you have a dual space. And this is a space of operators on these V's, okay? This space is a different space, has different operations, okay? Because it's a different space, cannot have the same operations, and has a different basis. Different elements. The red elements are not in V, are in V star. Okay? And then you can apply, you can define and relate them in a way, so you can find a base if it's a dual space that satisfies this thing. But notice, the one with the index up are operators. The one with the index down are vectors. Okay? Are two different things. So I can apply an operator to the vector, and if the index are the same, is 0, 1. That's what I'm talking about. So, and then you know that a vector can be a linear combination of elements in the basis. This is standard linear algebra. But in the dual space, that's different, right? So it's a different space, you have a different basis, you have different numbers. These Rn there and these Rn there are two different they represent completely different objects. They are different objects, okay? And this pairing, this natural pairing, which in quantum mechanics is used by Dirac, introduced the Bragg-Katz notation, which is nothing else than the natural pairing of these two objects. Because if I give you an F and I give you a V, I can give you power without any inner product that is not there. Is not there the inner product. Okay. These are called covariant. You see, the basis of the vector space and the real numbers of the covector space change coordinates in the same way. And these are called contravariant. They change the opposite direction. If you have changes of coordinates which are not orthonormal, these are different. And whenever you have curvature, this is why Einstein used, differential geometry, because when you have curvature, the coordinates is not just, everything is not orthonormal, okay? If you have an inner product in the first place. So this is an invariance concept, and vectors, therefore, are different elements. And these are the matrices stuff I told you. Because if you don't understand this, I give you a matrix, you just take an eigenvalue. But a matrix is not a mathematical object. What the hell does it represent? If it represents a map between a vector space and a vector space, I can calculate the eigenvalue as we do usually, and it makes sense. If it's a quadratic form and I calculate the eigenvalue, you get numbers which you can throw in the bin, trash bin, because it makes no sense. Okay? And in robotics, for example, as I said a number of times, forces and velocity are not the same. When you have a Jacobian and a Jacobian transpose and they multiplied, you just create mathematical bullshit because you map something to something, and then you take an operation and get something else, and you just map it. It's juggling with numbers. Okay. So pairing in mathematics is basically I give you two things, and you give me a real number associated to these two things. So if I give you a vector space, I know I can build a dual vector space. I need no structure, no extra structure. I can define a space of linear operator on this vector space. And then I can define duality by saying, okay, I just apply one element to another. They basically kiss each other. It's like men and women. It's like natural. But if I give you two elements in the same vector space, okay, I can do nothing with them. I can do nothing with them unless I give you an extra structure, which is an inner product, which is a Hilbert structure. I mean, this is standard linear algebra. Standard linear algebra. This is the Poincaré stuff, duality, and that's Hilbert stuff with a Hilbert structure. About topology and geometry. There's a big difference between topology and geometry. And I think that a lot of advances in physics, in engineering and physics, is because people just mix it. In topology, a sphere and ellipsoid, topology doesn't have shape. This cup, this sphere, and this ellipsoid are the same object in topology, are equivalent, completely equivalent. You cannot distinguish between them. But once you fix distances, a sphere is different than an ellipsoid. Okay, so the shape, fix the shape, that is geometry. And the two are related, okay? The very famous Poincaré conjecture, actually solved by Paderman, actually used what is called the Ricci flow, which connects these two things. But these are very different concepts. I'll come to back that later. But it's important to realize that topology and geometry are two different things. Now let's go to ports. If I give you a physical system, and I want to decompose, because that's what an engineer can do, okay? This is, I'm working on some stuff, advanced stuff in physics, which I realize that people have been looking for a long time without finding, because they do not have the engineering approach. In engineering, we know we decompose things, like Descartes taught us. So if you have a system you want to decompose it, like, a mass spring system, you want to write there's a mass and a spring, okay? And then understand the mass, understand the spring, and then describe how they are attached. You want to divide it in two parts, and you want to do things not forgetting energy, because energy is important, as I told you before. So if the total system has a certain energy, I want to say, when I decompose this, I want that this part has that energy, this part has that energy, and the sum of the two energies is the one I started off with, okay? Because I want to be consistent in my decomposition in energy. So whatever I do, and the question is, how do I describe how they interact between the two, okay? Because the total energy should be always the one we started off with. Well, if I take the time derivative of it, it means that when the energy goes down here, it goes up here, or the other way around, right? So I can talk about power transfer. So it means that if the energy goes down here and goes up here, it's because there is a power transfer from one to the other, right? And then the question is, all right, but then there is another reason that, the two systems, why should be one better than the other? They influence each other. This is a matter of physics. Okay, action-reaction. So I just call whatever that is, I don't know what mathematically E and F are just two things. Causality speaking, part one gives the E on, is an input, is an output for one and an input for two, and the other way around, okay? And the question is, what is the nature of E and F? Okay? What is the nature of E and F? And the answer is very simple. We need a pairing which is intrinsic, which doesn't have any structure extra. What would that be? Duality. So E and F are two vector spaces, and why this should be vector space, I don't have the time to go into, but there are reasons why these are vector spaces. And they are dual. So if you give me an E and an F, they can kiss each other. The value they give me is the power transfer between the two. And this is true not only for finite dimensional spaces, but also for infinite dimensional spaces, because this is the way nature works in all domains, finite and infinite dimension. Duality is the most important thing I've ever learned in my life. And this is just the concepts that was translated to a bond in bond graphs, but of course that time all this stuff was not known mathematically speaking, but this is how basically the physics behind the conceptual genius of Paynter to see this ahead of time. Okay? And this is true for any possible domain. Now, geometry is important. You know, this painting is a Raffaello painting which is in Vatican, and what is basically represent the academy. I mean, to have been in Greece and show this is, this is the right place to appreciate this. And what is written, and what was written at the entrance of the Academy of Plato is Geometricus medias cito. I hope I pronounce it in a decent way. But what basically said that geometry is, don't let the ignorant of the geometry enter, which of course was not the geometry in the sense we use it, but geometry was for the old Greeks was like something secret, so it was intelligence, the reasoning was there. But I think that they also saw ahead of time how important geometry actually is. If we have if we want to connect something like this with two rigid bodies and body, what we would do is say, okay, an amplifier and a motor are connected with the voltage currents because the product of these two is power. And these are scalar, no geometry yet. If we have a motor and an axis, you have that the torque and angular velocity are also to real number to scale, no geometry yet. But once you go to rigid bodies, you need to start thinking about geometry. It turns out that, Lie algebra and Lie groups play a role there. Okay? These are basically vectors, representation of certain things. So all this stuff on forces and velocities, okay, are important. But the point is, can you generalize this to infinite dimensional systems in a way which is very general in all possible situations? And I see that, I have to quickly go through it, but I will try to give you an idea how that is done. Okay? And the issue is to make a difference between what is geometry and what is topology. Okay? And you need a covariant way of doing this. So the idea was you have the fluid, you have the wing, you want the interaction between the two, you want to describe this port on the boundary of this wing. And the goal I put for myself was this should work in all dimensions, not just for any dimension, not only for the space we live in, completely coordinate free, applicable to all physical domains, and possibly in curved spaces. And this brought to the use of exterior calculus and differential forms. It's pretty sad, besides linear algebra, another thing which frustrates me, is that we teach our students, when we talk about calculus, we teach Riemann integration. Riemann integration is the worst way you can teach Riemann integration at first place. Integration is a purely topological thing. There's nothing to do with geometry. And Poincaré saw it right. And these two gentlemen, okay, Grassmann and Cartan, invented this calculus, quite a long time ago, okay? And this is really the coordinate invariant way to do integrations. What are these forms? Okay. Well, a form is a multilinear operator. Okay, multilinear operator which is totally skew symmetric. Okay. So it basically eats vectors and spits a real number. Okay, it eats a k form eats k vectors and spits a real number. And if you invert the order of two of these vectors, you get a minus the previous number. Okay. So if you would use coordinates, basically, a 0 form would be just a function on a manifold. A 1 form would be something like that, a row vector kind of stuff. A two forms would be a skew-symmetric matrix, and you can imagine what the rest would be. And integration, what George Deram showed in details, is nothing else than the natural pairing between a form and the object you want to integrate upon. We know what it means to have the value of a function. If I give you a space and I give you a function on that space, what does it mean to evaluate the function? You say, at that point, the function has that value. At that point, the function has that value. It's just a generalization of this, but instead of a point, I want this for curves, for surfaces, for higher dimensional things. So a function is a zero form you evaluate on a point. A one form is an object you evaluate on a curve. A two form is an object you evaluate, etc., etc. This is exterior calculus. So it's nothing else than the generalization of function evaluation, okay, to higher dimension, okay. And then there is also something between a difference between forms and pseudo-forms. I don't have the time to go, I will skip this. But then there are three operations that you can do with this object. The first one is this, it's called the wedge, which is the wedge you may have seen in integration in the past. If I give you a K form and an L form, I can define with this operation a K plus L form. What does that mean? It means if I give you two objects that you can integrate on curves, one on a curve and one on a curve, I can define an object you can integrate on a surface if I take the wedge, because 1 plus 1 is 2, is a two form, you can integrate it on a surface. That's what this operation does. Then you have a D, which is the differential that you all know, but then casted in a proper setting. And this is a purely topological operation that basically relates how things are related when they are close by each other. It's a topological thing. There is no metrical stuff whatsoever. And finally, there is another operation, which is called the Hodge star. This is Hodge theory, which basically goes from a K form to n minus K pseudo form, but let's say a form. So basically it takes the complementary dimension of the space. So if you have a three-dimensional space, and I give you a one form, you take the Hodge, you get a two form, okay? These are all the operations. The topological things is represented by Stokes' theorem, okay, which is in this way is properly formed. You need one formula to do all calculus rather than all these names, Gauss, Green, or whatever names they use when they use vector calculus. And the inner product is the L2 norm, and so it's actually, you can use it as an L2 norm in this space. So you basically have two things. You have a topological stuff, duality, which is Poincaré stuff, which is, you see, you give me a K and an n minus K thing, you get an n thing, and you can integrate on the volume, on the dimension. That's the duality. These two forms are dual, and the upper one is instead are two vectors, like two vectors, a vector and covectors. That's what it is. And, vector calculus, as is taught still today, okay, was found out by Maxwell at the end of the 1800s, okay? And he uses these symbols. I mean, it was a genius that he found that, but it was a while ago, okay? And it has a lot of problems because it only works it mixes topology and geometry. It doesn't generalize the dimension higher than 3. In fact, that's why in gravity used forms. No clear information of orientation. It's just, but then. And this is what we do. This picture shows you a bit of history, okay, of science, okay. We are now 152 years later than when vector calculus will find, we still teach vector calculus, when instead a number of people have shown that there are much, much better things to work with. 171 years later than Riemann introduced integration, as he did, we have much better things to do that, and we still teach a Riemann integration. I think we should look at this stuff. But what we can do is to make this step to something that actually can generalize to everything. First of all, we can recognize this as basically two directions. You go from function, vectors, the rotation and divergence and all these operators, and to go back. But the real magic happens when you realize that these are just nothing else than what is called the de Rham complex. What you basically have, that functions are zero forms. I told you before, right? And the dual of a function in an n-dimensional space is actually what is called an n-form. You can show this stuff, okay? A vector field can be represented by a one form. Okay, and then you have an n-1 is related to that, but is a pseudoform. So this structure, you see the odge goes from up to down. That's the metrical structure, okay, that relates these two things, the inner product, that creates the duality between these two things. But the up and the down line are vectors, covectors, are dual, okay? And the relation in vertical is given by metrical structure, the odge. But the relations along the line in both directions is only the D, and that's a topological thing. These are forms, these are pseudoforms, this is topology, and this is geometry. Once you understand this, the magic starts happening. If you look, for example, at Maxwell equations, okay, these are the way to write Maxwell equations without this, these terrible things that Maxwell himself geniusly found, but it's become old. Because these are the Maxwell equation. The electric field is a one form, okay? If you take the D of the electric field, you get a two form. I told you, if you take the D, you increase the order of one. It's a two form, which is the B field, okay? If you have an H, the magnetic field, if you take the D of that, you get the electric field induction, okay? And the B and the H are connected by an odge, which is the mu odge. And the electric field, which is called the epsilon odge. From this, you can read the electric energy is nothing else than the natural pairing of the two columns. The left column, the wedge of these two, the wedge from the one form and the two form, gives you a three form, right? You can integrate that object on a space, on a volume. That is the electrical energy in that volume. If I give you the right column, and I take the wedge, okay, I give you a three form again, because the top one is a two form, the bottom one is a one form, 2 plus 1 is 3. You integrate it on a volume, you get a real number. That real number is the magnetic energy of that volume. Not only, if you take the diagonal, you get a two form, you see? 1, 1. 1 plus 1 is 2. Do you recognize what E wedge H is? Is the Poynting vector. Is the energy that flows out of that volume. So basically you can, with these things, bring pores to physics in a very nice way. These are efforts and these are flows. And the wedge is the natural pair between vectors and covectors. And once you do that, you can express any physical system in any dimension by making very clear what is topology and what is geometry. And you can talk about energy storage, flux through the boundary, or flux inside the volume. And this is perfectly fine to do basically 90% of the physics out there. But if you go to elasticity, you have a problem. Because in elasticity, you have something which is called the rate of strain, which is a symmetric tensor, and you cannot represent it with this. So you need to adapt. So you need to look at forms which do not only have a real value, but have a tensor value. And this object is the most geometrical object to describe all the realm of physics, from basic mechanics to quantum to gravity to everything. And you can define the pairing in a different way. I will skip this, forget about this. You can define a proper pairing of these objects, but I will skip it. And this actually brought to these publications on nonlinear elasticity. I mean, are not easy to read publications. The one on the left is, I think, 40 pages of decent math. So, but it's all there. It's all there. And then the question was, okay, that's great. We have finished this field stuff. Let's go to discrete things. And then we figured out the dual fields. I gave this plenary at the Centre International de Recherche en Mathématiques in Marseille, which is online. So if you want, you can see that. That explains these things. And I want just to share with you very briefly the idea. So all fields can be represented with these forms. So if what you do with discretization, you mesh the space, okay? You create a mesh in which you want to discretize spatially wise your thing. This is done in these settings with what are called cochains, okay? And then you triangleize everything, and then you reduce that to numerics. You go from an infinite dimensional to a finite dimensional numbers, representing that on the mesh. If you then re-interpolate that, you go from the numerics to, again, basis function, this is finite elements models, that basically, you see it's like a subspace. The orange one is subspace, which is spanned by your functions that you use for a finite element model. And basically, you connect an error in order to discretize. Okay? And then you can show that if this property is preserved, so basically if you can commute this projection with the D operator, you have what is called structure-preserving discretization. This is the way that people should discretize PDE, because this is structure-preserving, doesn't create mistakes, doesn't create errors. And it turns out that with some other tricks which I have to skip, you can get basically to do equations. If you have a notch, you have metric structure. Well, we figured out a way to say, good, you have a metric structure. If you give me the initial conditions in that metrical space, you can integrate the PDE forgetting about the metrical structure. Okay, it's magical. It's very, very cool. And then you have the highest precision you could imagine. So, dual field is, the spatial discretization has really a number of advantages which are really has not been there. So we also work on a practical thing. We work, as I said, on actuators, on control of certain oscillation for the wings. We did a lot of fluid dynamics and measurings in the wind tunnel. I had to buy a thing which cost 250,000 euros to create these bubbles. And I will conclude, well, I'll skip the video. If you're interested, I can show you later this video. But I want to actually conclude with some ideas in conclusion. True knowledge comes with deep understanding of a topic and its inner working. Albert Einstein was one of the biggest people in science ever, and he saw it completely. Okay, I think that port-based really resulted in substantial fundamental contribution in this business, and I'm really happy and proud to have been in contact. First I didn't get the point, and now I cannot think otherwise. Okay, and port-based thinking was really the driving force behind everything which I presented, and these of course now open new ways of doing model reduction, control, and other stuff in these settings. And now I'm working actually on the connection between quantum field and gravity, and I told somebody I really think I found a way to do it. So I'm working day and night on the publications that hopefully I will disclose soon. My personal advice to conclude with, I'm convinced that the great breakthrough are really to find the right mathematical structures. Okay, not too much, not too little. If you have too little, you don't have enough expressivity to do what you want to describe. If you have too much, like Rn, you may do things that make no sense. You need the right structure. Let the mathematic structure guide you, because if you know you are in the setting with the structure is okay, and you know that you can do certain things, so to speak, you could try it out, and you know that makes sense, whatever it is, whatever that is. Be critical, nevertheless, on each step, of course, okay? And also ask you why. But do not kill your creativity in doing that. My experience has been, people sometimes are, just go for it and check it if it's invariant, okay? So I think that epistemological growth is not about solving a problem for academics, but it's understanding why and how to solve the problem. Thank you very much.